Most people walk past roadside outcrops without realizing that weathered basalt or rhyolite with minor pitting might conceal valuable amethyst pockets. The opportunity is subtle. Where erosion cuts through volcanic rock, especially in road expansions or landslide zones, the chance of exposing geodes or mineralized cavities increases dramatically, but only if you know what to look for. Start with visual habit. Amethyst forms as a variety of quartz, typically within gas bubbles in volcanic rock. These vesicles over geologic time are gradually filled with silica-rich hydrothermal fluids which crystallize into quartz. In specific conditions, low iron, stable temperatures, these become purple, amethyst. Look for gray to brownish spherical or oval shapes embedded in matrix, often about the size of a fist to a basketball. They might not shine, but subtle concentric rings, a slight shimmer, or pocked texture hint at internal crystal growth. Surface erosion plays a key role. In road cuts or construction zones that slice through ancient lava flows, you may find vesicular basalt with residual clay or iron staining. The outer shell of a geode is often dull, chalky, or coated in red-brown goethite. Tap gently. If it sounds hollow, that's a sign. Resist cracking it open immediately. Better to test systematically. The field logic here centers on terrain exposure and timing. Recent rains can wash fine sediment away, revealing geodes that were hidden days before. Roads that cut across flows older than 20 million years, especially those with visible vesicles or flow banding, are high-priority targets. GPS logging and field notes help build a grid, document where textures change, where clusters occur, and what angles the host rock tilts. But not all crystal interiors are purple quartz. Some hold chalcedony, agate, or clear quartz, so every candidate demands verification. Still, just one correctly identified amethyst-bearing geode in the right zone can signal a larger pocket system nearby. The question is, what distinguishes an ordinary rounded stone from a crystal-rich geode before you break it? It's easy to dismiss a weathered, egg-shaped rock as unremarkable until you know how to read its external clues. Many amethyst geodes look like dull, featureless nodules on the outside, yet conceal spectacular interiors. The trick is to recognize form and surface texture, not color, as your first line of evidence. Amethyst frequently forms inside vesicular basalt, rhyolite, or volcanic tuff where trapped gas bubbles once created empty cavities. Over millions of years, these cavities filled with hydrothermal fluids rich in silica and trace elements like iron. The result is a geode, an internal crystal lining protected by a hardened shell. From the outside, these geodes can be spherical, flattened, or slightly elongated, with diameters ranging from a few centimeters to over a meter in rare cases. What gives them away isn't color, it's pattern. Many have a cauliflower-like or knobby texture. Look for micropits, subtle banding around the exterior, or a chalky white rind. In areas with known volcanic activity, rounded rocks with a gritty or vesicular surface should never be ignored. Sometimes, tiny quartz points protrude from cracks. These are high-potential indicators, even if color is absent at first glance. Weight also matters. A solid basalt nodule will feel denser in the hand than a hollow geode of similar size. Seasoned collectors develop an intuitive feel for this. When in doubt, use a water displacement test in the field. Weigh dry, submerge fully, and record volume displaced. If the calculated specific gravity is significantly lower than solid basalt, (2.931), it may be a cavity. Some of the most valuable amethyst clusters have come from seemingly insignificant exterior stones. The famous Uruguayan deep purple geodes, now worth hundreds per kilo in raw form, were first extracted by breaking open weather-worn nodules along eroded creek beds. And it's not just in South America, regions of Mexico, the U.S. Southwest and Morocco have similar geode-bearing strata, often misidentified for years as common volcanic rubble. Before you move on, mark, photograph, and sample carefully. Splitting a geode in the field is risky. It can damage valuable points and destroy evidence of growth zoning. better to flag the specimen, collect nearby float material, and return with proper tools if it shows promise. The next question becomes, which specific geological settings consistently produce these promising shapes, and why? That's where volcanic and hydrothermal mapping makes all the difference. The richest amethyst formations don't appear randomly. They follow the logic of volcanic history and hydrothermal flow. Understanding where and how amethyst crystallizes in nature means reading the terrain like a layered map of ancient activity. The key lies in locating zones where silica-rich fluids once traveled through porous volcanic rock under precise thermal conditions. Amethyst is a variety of quartz, CO2, that gains its purple hue from trace amounts of iron Fe3, substituted into the crystal lattice and subsequent exposure to natural radiation. This process happens in volcanic regions where rhyolite, basalt, or andesite flows have cooled and fractured. The cavities, created by gas bubbles or tectonic movement, become vessels for mineral-rich solutions. As temperature and pressure decline slowly, quartz begins to crystallize from the inside out, forming concentric growth zones. When iron is present in the right oxidation state, and radiation levels are stable over time, amethyst forms instead of clear or smoky quartz. There are two dominant formation settings: amygdaloidal basalt flows and hydrothermal quartz veins. In the first, amethyst grows inside gas vesicles in lava that later become geodes. These are common in flood basalt provinces like the Paraná Basin in Brazil, the Deccan Traps in India, or the Mid-Continent Rift in North America. In the second, amethyst lines fractures in volcanic rock or sedimentary beds near fault zones, where hot silica-rich fluids deposited crystals along the walls. This occurs in areas with past geothermal or epithermal activity, often adjacent to ore systems or hot spring deposits. Recognizing these host environments starts with rock type and layering. Fine-grained, dark basalt with rounded vesicles signals former lava flows, especially if overlaid by ash or ignimbrite. A pattern of thin, parallel veins cutting across this matrix suggests hydrothermal activity. Look for oxidized zones, often red, yellow, or black staining, along these fractures, which may indicate fluid pathways. Drainage patterns help too. Exposed cliffs, eroded stream banks, or landslides in old lava fields can uncover long-hidden pockets. If a cluster of geodes turns up downstream, trace it back by mapping tributaries and studying changes in float composition. A shift from common quartz to purple fragments is a reliable escalation point. Geological surveys can accelerate this process. Many national geological databases publish old mining maps showing past mineral claims, lava field extents, and fault zones. These overlays, combined with field observation, can reduce weeks of blind searching to hours of targeted prospecting. Bright red stains on fractured rock faces may look like simple rust, but in the right geological context, they're among the most reliable surface indicators of amethyst below. The connection between iron oxides like hematite or goethite and the purple tones of amethyst isn't cosmetic, it's chemical, and it tells a deeper story of the crystal's formation. Amethyst coloration originates from iron impurities, specifically Fe3, within the quartz crystal lattice. But that iron didn't appear randomly. It traveled with the same silica-rich fluids that deposited quartz in open spaces. In many hydrothermal systems, the outer edges of these cavities or fractures accumulate iron oxides as a byproduct of chemical precipitation. When the fluids cooled or oxidized, the iron crystallized separately, coating walls, sealing microfractures, or concentrating in porous zones. What you see on the surface as red, brown, or even iridescent staining is often the halo surrounding deeper mineralization. In amygdaloidal basalts, the logic is similar. The outer shell of a geode may show reddish streaks or blotches where iron-rich fluids first entered and began depositing material. These oxidized coatings are often more weather-resistant than the surrounding matrix, creating a slight textural rise or discoloration, especially noticeable after recent rainfall or fire-cleared vegetation. In such conditions, hematite's deep red or purplish hues stand out on gray-green rock, especially along fracture lines or vesicle rims. Field collectors should prioritize zones where multiple indicators converge: porous volcanic rock, vesicular texture, and iron staining along cracks or surfaces. In dry creek beds and erosion gullies, check where iron-stained cobbles accumulate. These are often the float trail pointing to a vein or pocket upstream. Magnetite may also be present, and a simple magnet sweep over fine concentrates can help distinguish between iron-rich and silica-dominant zones. The key field test is pattern, not presence. A single iron stain doesn't guarantee anything, but clustered stains that follow linear fractures, especially with subtle quartz infill or botryoidal coatings, are high-probability signs. In these cases, carefully prying open a fracture with tools or examining the surface under magnification can reveal microcrystalline growth, druzzy quartz with slight purple tint, indicating early-stage amethyst formation. Even when amethyst isn't fully developed, hematite presence suggests the chemical conditions were close. Some of the deepest purple amethyst from Thunder Bay, Canada, for instance, forms alongside massive hematite layers, creating striking bicolor specimens. The presence of red in these contexts is a literal red flag worth pursuing. A vivid purple hue can be deceiving in the field, especially when nature, industry, and fraud all produce similar-looking materials. Differentiating genuine amethyst from purple fluorite, colored glass, or synthetic quartz begins with field-accessible tests that rely on tactile, optical, and mechanical properties. Each test narrows the field of candidates, ruling out fakes long before lab work is needed. Start with hardness, the most definitive field measure. Quartz rates a 7 on the Mohs scale. If the crystal can scratch glass, typically tilde 5, or resist scratching from a steel knife blade, it passes the first filter. Purple fluorite, by contrast, sits at just 4, easily scratched by a knife. Colored glass often falls between 5 and 6, and will typically show signs of edge wear or chipping inconsistent with natural fracture patterns. Luster is another tell. Amethyst shows a vitreous, glassy sheen, but with a slight softness compared to glass itself. It lacks the mirror-like brilliance of glass and doesn't have the waxy or greasy look of some synthetics. Under magnification, real amethyst reveals growth lines, subtle zoning, and occasionally internal fractures called healed veils or wisps, none of which appear in uniform synthetics or molten glass simulants. UV light adds nuance. While amethyst doesn't fluoresce strongly under long-wave UV, some specimens may show weak bluish or white glow due to trace impurities. Synthetic quartz sometimes glows intensely or inconsistently. Fluorite, however, is often highly fluorescent, showing blue or violet under UV, a dead giveaway if you're testing a purple specimen in doubt. Then there's weight in hand. While not quantitative, experienced collectors develop an intuition for heft. Quartz-specific gravity feels heavier than most fakes of similar size, especially glassy imitations or dyed plastics. For more accuracy, a simple specific gravity test using a digital scale and water displacement can confirm. If your field result clusters around 2, 6, 2, 7, quartz is likely. Anything lower 2, 4 warrants suspicion. A final critical test is cleavage and fracture. Quartz breaks with a conchoidal fracture, smooth, curved surfaces with sharp edges. Fluorite cleaves in perfect cubes or stepped surfaces. Glass may mimic conchoidal fracture, but typically lacks internal growth zoning. Using a loupe or magnifier, scan for chevron patterns or color zoning inside, common in amethyst, absent in imitations. Each test is low-cost, repeatable, and rapid, ideal for field decision-making before committing to collection or transport. And while a positive ID boosts confidence, the real value question still looms. What characteristics within genuine amethyst mark higher quality or commercial worth? Scattered fragments of purple quartz in a dry creek bed might look like isolated finds, but they're often the first breadcrumb trail back to the true source. Expert amethyst prospectors know that erosion distributes float material downhill from its origin, and learning how to read this dispersal pattern can mean the difference between a handful of crystals and locating a mother vein or geode field. The process begins with recognizing amethyst float in all its variations. Tumbled, water-worn fragments are common in active drainages. They may appear pale due to UV exposure or iron coating but can still yield clues. Look for angularity. Sharper edges suggest a source nearby, while rounded pieces indicate longer transport. Color zoning, internal phantoms, and broken terminations help confirm that the fragments are indeed amethyst and not dyed quartz or fluorite. Once identified, these fragments become a directional tool. Work upstream, checking gravel bars behind large rocks and at channel bends where heavy materials like quartz concentrate. Use a classifier or hand sieve, 20 or 40 mesh, to isolate the heavier fraction, then a batte or gold pan to remove lighter matrix. Quartz is heavier than most river sediments but lighter than magnetite or hematite, so you'll find it mid-pack in the concentrate. In purple-rich drainages, even tiny shards show up consistently in the pan. When they vanish, you've passed the source. Use a topographic map or GPS to mark each collection point. As you move uphill, note changes in rock type and float density. If purple quartz begins to appear with host matrix, basalt, rhyolite, or welded tuff, you're getting close. In many cases, the slope narrows into a draw or vertical cut where the pocket was first exposed by weather or landslide. Watch for iron staining, vesicular textures, or exposed vugs in the cliffside. In successful cases, the primary source will appear as a cluster of geodes embedded in fractured volcanic rock, often in bands or layers consistent with old lava flows. Document the position, orientation, and spacing. These details matter for potential follow-up or legal declaration if the site holds commercial value. But not all float leads to intact formations. Sometimes you'll hit a scatter zone without a visible pocket. In those cases, the next step is to understand whether the terrain has shifted, been buried, or if you're simply on the edge of a larger structure yet to reveal itself. Mapping is critical. Finding float is only the beginning. Systematically confirming whether it connects to a productive amethyst source requires a structured approach. This phase transforms curiosity into controlled prospecting. Without a clear method, promising signs are often misread, and high-grade material can be overlooked just meters from the surface. The workflow starts with establishing a sampling grid. From the last confirmed float point, create a transect lineup slope, ideally aligned with natural drainage or fracture patterns in the bedrock. Place marker flags or GPS points at consistent intervals. 10 to 20 meters is standard in steep terrain. At each station, collect surface samples, record rock type, and note any changes in float composition. Concentrations of iron-stained vesicular basalt or rhyolite alongside purple quartz fragments should immediately trigger deeper attention. Use a sledgehammer and chisel to investigate any surface vugs or suspect fractures. If you uncover a pocket, note whether it's sealed with secondary minerals like calcite or goethite. These may obscure amethyst underneath. Photograph and label everything. Every broken nodule, even if barren, contributes to your understanding of how mineralization behaves on site. Deploy your sieve and pan again, but this time not in the stream. Use them on soil from shallow test pits, 30-50 cm deep, dug along the slope gradient or near fracture zones. If fine purple quartz persists in these samples, it suggests proximity to an undiscovered cavity or vein. A portable magnet can help isolate accompanying minerals like magnetite or ilmenite, which may point to nearby hydrothermal alteration zones. Track the directional trend of your finds. If multiple sampling lines yield consistent float in a north-south or east-west orientation, you're likely mapping a vein system. Veins often follow structural weaknesses like faults or bedding planes. Knowing the angle and direction helps predict where new pockets might lie. Use a geologic compass to log these orientations. Vein dip and strike patterns can later be compared with known productive belts in the region. Crucially, don't rush to dig deeply at the first sign of color. Some of the best finds occur in shallow pockets overlooked by those chasing depth. Systematic shallow sampling combined with accurate mapping offers better returns than blind trenching. Where deeper excavation is necessary, probe gently along natural breaks. Many geodes are delicate, and improper technique can shatter valuable clusters. All data, location, float type, mineral association, soil concentration, bedrock exposure, should be consolidated after each day. Only when trends emerge is it time to commit to heavier excavation or to bring in specialized tools like diamond saws or percussion drills. Every serious amethyst prospector eventually confronts a setback that looks promising on the surface, until a key test reveals the truth. The most common misstep: misidentifying purple fluorite, synthetic quartz, or even heat-treated stones as natural amethyst. These false positives aren't just embarrassing. They can lead to wasted labor, ruined specimens, and bad data that corrupts your grid. The most deceptive culprit in the field is fluorite, which can form in similar cavities, often with a vivid purple hue. Under certain lighting, it mimics amethyst almost perfectly, but its physical behavior quickly gives it away. Start with the hardness test. Quartz clocks in at 7, fluorite crumbles under a knife at just 4. If you're uncertain, test against a clean window pane or tempered glass. If your sample fails to scratch it, move on. Even more confusing are irradiated quartzes, colorless quartz artificially turned purple via gamma radiation. These can show impressive clarity and zoning, but their internal structure is usually too clean. Natural amethyst often contains chevron growth, minor inclusions, or color zoning that subtly shifts with light angle. If a piece looks too perfect, especially with a uniform grape-like hue, apply suspicion. In some regions, particularly near industrial zones or tourism-heavy locales, you'll also find colored glass fragments dumped or weathered into stream beds. These may appear as frosted purple nodules, mimicking water-worn amethyst. Hold them up to sunlight and rotate. Glass will often show curvature or bubbles under magnification. It also lacks the characteristic conchoidal fracture of quartz. Real amethyst breaks with sharp, curved surfaces, while glass edges tend to blunt with time. Then there's dyed quartz, often sold as enhanced amethyst or passed off as natural. This material starts with milky or clear quartz and is pressure dyed to a deep purple. A quick acetone rub on a cotton swab in the field can sometimes lift dye from the surface, especially in crevices. If water or sweat causes any color bleeding, or if the color pools in cracks, it's not natural. One of the most frustrating cases comes from zonally heated amethyst. Naturally purple crystals subjected to heat, either by wildfires or intentional roasting, can fade to pale yellow or brownish tones. These are often misclassified as citrine or smoky quartz. Careful visual inspection under LED light may still reveal faint phantom zones or chevrons typical of amethyst growth, offering a clue to their original identity. The lesson is hard but essential. Field enthusiasm must be tempered by methodical testing. Every time a suspected vein or pocket is found, run your basic field suite: hardness, UV, luster, fracture, and magnification. Keep a known amethyst specimen in your pack for side-by-side comparison. And if you're in doubt, isolate the sample until proper lab checks can be done. Sometimes it takes a failed sample to uncover the truth, that you're closer to a rich discovery than the signs suggested. In fieldwork, false positives don't just test your technique. They can trigger a major reversal in assumptions that reframes the entire search area. One of the most revealing moments comes when a suspected fake turns out to be real, or vice versa, and it forces a reassessment of the terrain. That turning point often hinges on subtle shifts in the matrix-host relationship. You might have dismissed a zone due to pale color or odd fracture patterns, assuming it was non-productive. But upon breaking open a larger nodule or using better light, you spot the faint chevron banding of genuine amethyst, or discover that your dull fragment aligns perfectly with a known amethyst-bearing rhyolite layer just meters upslope. That's the reversal, and it reshapes the grid. A real-world case. In the Four Peaks region of Arizona, early diggers mistook heat-faded amethyst for low-grade quartz due to forest fire damage. It wasn't until someone sent in a pale specimen for spectroscopic analysis that they confirmed it had once been deep purple. That zone, once dismissed, became one of the richest sources of American amethyst, now commanding over $50 per carat in finished form. Reversals like this demand recalibration. Go back to the rejected samples and reassess them under controlled light. Use a bright white LED and observe zoning, fracture behavior, and UV response again. If phantom zones emerge or the color intensity shifts under polarized light, the stone is natural. A thermal conductivity probe or Raman spectrometer, if you're equipped, can eliminate synthetics immediately. Even basic digital microscopes in the field can reveal zoning patterns that are invisible by eye. Revisiting the host rock is equally important. Sometimes the amethyst doesn't form in obvious cavities. It lines narrow seams in brecciated basalt, barely visible until the rock is slabbed. Or it appears as scepters growing on clear quartz, overlooked because the color appears in only one section. These hybrid formations often fetch a premium among collectors, but are easy to miss in situ. When a suspected dud becomes a confirmed source, update your map with a different lens, not just where crystals occur, but where the conditions for their preservation exist. This includes slope aspect, was the north face shaded from heat, overburden depth did glacial till obscure the vein, and exposure quality. A vein might yield nothing at one outcrop, but show deep purple 20 meters away. Ultimately, these reversals sharpen your sense of terrain logic. What looked barren now signals potential. What seemed like float might have broken from a vein just beneath your feet. And with each corrected assumption, your search gets leaner, faster, and far more likely to strike high-grade material. When informal tools hit their limit, professional-grade discovery depends on standardized methodology. Seasoned prospectors and geologists don't just rely on instinct. They rely on protocols built from decades of mapping, sampling, and repeatable results. These methods, developed and refined by geological surveys and university-led field projects, are what turn a personal find into something with commercial, academic, or conservation value. The first anchor is grid-based sampling, adapted from mineral exploration standards. In this method, a known or suspected amethyst zone is divided into square cells, typically 10x10 or 20x20 meters, using GPS, tape measures, or flagging. Each cell is logged separately, and at least 3 variables are recorded: rock type, float density, and visible mineralization. This method reduces bias toward eye-catching specimens and helps identify subtle trends in crystal occurrence. Next comes systematic trenching or core drilling, depending on terrain and permissions. In areas where float suggests buried geodes or fracture-bound amethyst, geologists often excavate shallow trenches perpendicular to the suspected vein trend. Each trench is cleaned, photographed, and mapped in profile. Every exposed cavity is noted for orientation, depth, and mineral association. In commercial-grade cases, reverse circulation drills or diamond core rigs are used to retrieve subsurface samples without disturbing the surrounding matrix, a practice common in southern Brazil and Uruguay, where deep amethyst pockets hide under volcanic caprock. Then there's mineralogical correlation. Using X-ray diffraction, XRD, scanning electron microscopy, SEM, or even handheld Raman spectrometers, field teams can identify the precise mineral assemblage around the amethyst. If you find consistent co-occurrence of minerals like calcite, hematite, goethite, or zeolites, you can start to model the hydrothermal system that formed them. Institutions like the USGS or CPRM in Brazil often publish these assemblage models by region, linking known geology to typical quartz varieties found there. Remote sensing and GIS integration have transformed how these discoveries scale. Using satellite imagery, multispectral data, and terrain models, experts can overlay known amethyst occurrences with geophysical indicators, like magnetic anomalies or fault alignments, to predict where other pockets might be hiding. In India's Deccan Traps, This method helped identify overlooked lava domes now known to host cavity-lined amethyst in sheet flows. Field pros should also tie into geochemical soil sampling, especially in weathered terrain. Measuring trace elements, like Fe, C, Al, and Mn, in soil samples across a prospective zone can reveal buried hydrothermal alteration halos invisible at the surface. When aligned with mineral float and structural data, this offers a 3D picture of the potential resource. And perhaps most crucially, all of this is repeatable. A discovery that follows grid logic, returns consistent test results, and correlates with published geological models has far greater weight, both scientifically and financially, than an isolated crystal find. It enables partnerships, funding, academic publication, or even formal claim registration with governing bodies. No method, however precise, will yield results in the wrong terrain. Amethyst may be found on 6 continents, but its natural formation depends on specific geological circumstances, conditions that don't exist everywhere. To maximize efficiency, expert prospectors learn to filter regions not just by reports of past finds, but by matching terrain to the necessary volcanic, structural, and hydrothermal profiles. At the global scale, volcanic provinces are the primary hunting grounds. Amethyst thrives in areas with past or current basaltic and rhyolitic activity, especially where lava flows cooled slowly and trapped gas bubbles. These zones create vesicular textures, ideal for geode formation. Major sources include Brazil, Rio Grande do Sul, Minas Gerais, home to extensive flood basalt provinces, especially the Paraná Basin, known for large geode-lined cavities. Uruguay, Artigas region, adjacent to Brazil's basalt flows, producing some of the deepest colored amethyst on Earth. Zambia and Namibia, African sites with amethyst associated with quartz veins in metamorphosed volcanic belts. United States, Arizona, Colorado, Georgia, found in rhyolite-hosted cavities and hydrothermal veins, especially near known ore districts. India, Deccan Traps, vast basaltic regions with amygdaloidal textures, underexplored for amethyst but increasingly showing promise. Mexico, Guerrero, and Veracruz, famous for slender, transparent crystals in vuggy rhyolite with strong zoning and phantoms. Regionally, the type of host rock is your first filter. If your search area lacks volcanic rock, especially basalt, andesite, or rhyolite, it's unlikely to hold amethyst geodes. Sedimentary terrains, granitic massifs, or limestone-dominated belts are better suited for other minerals like calcite, barite, or agate. However, amethyst can still occur in hydrothermal quartz veins that cut across these rocks, particularly in areas with known geothermal activity or mineralization history. Climate and erosion exposure also matter. Dry or semi-arid regions with exposed bedrock and little overburden offer better visibility of float material and host rock. In contrast, tropical zones with thick vegetation and weathered laterite soils may conceal promising veins under meters of cover. That's where satellite imagery and soil geochemistry become indispensable. Legal access is another constraint. Even if terrain is perfect, land status can bar collection. Some of the richest zones lie within national parks, indigenous lands, or private mining claims. Professionals check geological maps against cadastral data before stepping foot on site. In places like Brazil and Madagascar, field collection requires explicit permits even for non-commercial research. And finally, consider the market history of the region. If a country has a documented amethyst trade, there's likely a network of informal knowledge, old diggings, and local specimens already circulating. In contrast, newly emerging sources, such as recent discoveries in Morocco and Ethiopia, often yield surprises because their terrain was previously written off. In short, terrain logic filters opportunity. Even the best tools can't find amethyst in the wrong rock. But in the right place, at the right time, a subtle slope or fracture can reveal what thousands missed. While amethyst belongs to the quartz family, its discovery shares surprisingly similar logic with high-value stones like diamond, jade, and opal, especially when it comes to recognizing indicator minerals and verifying primary formation settings. Comparing these suites helps sharpen your field instincts, not just for amethyst, but for differentiating mineral environments with overlapping features. Start with diamonds, which form in deep mantle-derived rocks like kimberlite and lamprite. These pipes erupt explosively, bringing with them indicator minerals like pyrope garnet, ilmenite, chromite, and spinel. None of these appear in amethyst contexts, but magnetite and ilmenite do occur alongside hydrothermal quartz, especially in iron-rich basalts or altered andesites. So while you won't confuse the two directly, the presence of magnetite in pan concentrates may still mark a productive silica system, just not for diamond. Jade comes in two varieties with distinct formation paths. Nephrite, a fibrous amphibole, is found in serpentinized ultramafic zones, often with minerals like actinolite, epidote, and chlorite. Jadeite, on the other hand, forms in subduction zones within high-pressure metamorphic belts. These rocks lack the vesicular volcanic textures where amethyst thrives. However, actinolite and chlorite can occur in hydrothermal veins, so if you see green minerals in your system, confirm it's not a jade belt. More importantly, in zones where both amethyst and nephrite have been reported, like parts of British Columbia, knowing the difference in host rock saves time and prevents misclassification. Opal's story is closer to amethyst-S. Both form from silica-rich fluids, but opal is non-crystalline hydrated silica. It fills voids in sedimentary and volcanic rock, often forming as common opal or precious opal with play of color. Its indicator suite includes kaolinite, calcite, and limonite, minerals also found near weathered quartz veins. The giveaway is texture. Opal is waxy, low luster, and soft, Mohs 5-6, while amethyst remains vitreous and hard 7. But geologically, areas with opal often host low-temperature hydrothermal activity, a clue that quartz varieties, including amethyst, may not be far behind, especially in older zones that underwent secondary mineralization. This comparative framework matters when exploring transitional zones, regions with overlapping or sequential mineralization events. For example, a volcanic caldera might host opal near the surface, amethyst in deeper cavities, and zeolite group minerals lining fractures throughout. Knowing which minerals signal which depth and temperature allows you to predict what's below before you dig. In the field, this means bringing not just tools for quartz, but a cross-reference kit. Streak plates, hardness references, UV light, magnet, and magnetite-heavy sand samples for baseline comparison. You're not just identifying amethyst, you're ruling out what is an amethyst based on associated minerals and rock context. Finding a promising amethyst zone is only half the challenge. The other half is staying safe and legal while you explore it. Whether you're in a highland basalt field or a flood-prone drainage, each environment carries risks that can jeopardize your gear, your samples, or your life. Professionals factor in safety and regulatory frameworks from day one, because a single misstep, on a slope or with a permit, can end a season's work. First, assess terrain stability. Many productive amethyst zones lie in eroded volcanic formations, where steep slopes, loose scree, and uncemented ash layers dominate. These areas become unstable after heavy rain or snowmelt. Before stepping into a gully or excavation site, check for undercuts, water flow signs, and tension cracks in overlying rock. If vegetation is sparse or tilted downslope, it's a red flag. Land movement is ongoing. Use trekking poles and safety ropes when approaching vertical cuts or ledges. Never work alone in active landslide zones. Then consider weather dynamics. Dry riverbeds and desert washes, ideal for float tracking, can turn deadly in minutes with upstream rainfall. Always monitor conditions in real time. In tropical zones, prioritize early morning work when heat, humidity, and lightning risk are lowest. At high elevations, be prepared for sudden temperature drops and ensure your pack includes emergency layers, water purification, and energy reserves. Legal access is another layer of protection. In many countries, mineral collection is restricted by land designation. National parks, Indigenous reserves, private properties, and registered mining claims all have rules that, if violated, can result in fines, confiscation of specimens, or legal action. Before collecting, consult cadastral maps and landowner registries. In Brazil, for example, even casual collection on federal land requires an exploration permit. In the US, surface rights and mineral rights are often separate. Owning one doesn't grant you the other. If you're working in a known amethyst-producing region, be aware of claim boundaries and active operations. Avoid trenching or sampling near flagged or marked areas without written permission. Many small-scale mines operate without formal signage, but are legally registered. Locals may grant access for a fee or share knowledge, but informal permission doesn't override land law. Also factor in wildlife and biological hazards. In some volcanic zones, venomous snakes, scorpions, or even bears are a real risk, particularly in North America, Africa, and parts of Asia. Insect protection, snake gaiters, and basic first aid training are essential. In tropical or subtropical areas, waterborne pathogens and plant thorns can pose greater threats than terrain itself. Documentation matters too. Keep a field log with timestamps, GPS coordinates, photos, and landowner contact if applicable. This not only protects your discoveries, but also establishes a record if questioned by authorities. If you're mapping or planning to publish or sell, clear documentation is your best legal defense. A handful of promising amethyst fragments isn't enough to confirm a viable formation. Real confidence comes from repeatability. Experts don't rely on lucky hits. They prove a site's value through grid-based verification, systematic testing, and geologic continuity. This phase separates casual collectors from serious field mineralogists, turning one-off finds into mapped occurrences. Verification starts with a test grid, ideally over the most promising quadrant of your earlier search. Lay out a square grid using tape measures, GPS points, or flagging stakes. Typical spacing ranges from 5x5 to 10x10 meters, depending on terrain complexity. At each node, perform a controlled surface inspection and shallow subsurface sample, logging the presence or absence of float, host matrix, and visual mineralization. Next, dig shallow pits or trenches, no deeper than 50 cm, to test the soil profile and collect bulk material for washing. This is where the sieve and pan process reappears. A consistent recovery of purple quartz fragments, vesicular basalt with quartz infill, or iron-stained chips confirms proximity to a vein or geode cluster. Document everything: grid square, depth, sample weight, and visual traits. If more than 30–40% of grid points yield positive indicators, your probability of a defined mineralized zone increases. For higher confidence, repeat the test along a perpendicular axis or at a new elevation contour. Often, a horizontal band of float or a change in slope reveals the true geometry of the deposit, a fracture-filled zone versus a scattered geode field. Use repeat photography, same location, angle, and scale over time, to monitor how erosion or seasonal exposure alters the site. Crystals that were partially visible may emerge fully after rainfall or freeze-thaw cycles. Time-lapse tracking adds dimension to your proof. The final step in verification is correlation. Match what you see to known geological models. Does your float composition match reported amethyst fields nearby? Does your host rock type align with published volcanic flow maps? Institutions like the USGS, CPRM, Brazil, or local university departments often have open access data. If your findings align with known structures, or better, extend them, you're standing on evidence, not assumption. Repeatability also matters for commercial or scientific partnerships. Museums, gem buyers, or academic collaborators won't invest based on photos alone. A site that can produce consistent samples over a known area, with logged coordinates and physical data, becomes viable for publication, protection, or resource valuation. In the world of gemstones, discovery is only half the equation. Value lies in quality. And when it comes to amethyst, grading begins long before the first cut. Professionals assess rough material based on clarity, color saturation, zoning, size, and structural integrity. Whether you plan to cut, sell, or collect, knowing how these variables interact determines whether a find is commercial grade or just geological interest. The first and most visible factor is color. High-grade amethyst exhibits deep, uniform purple with blue or red flashes under direct light. This saturation should extend throughout the crystal, not just concentrate at the tips or edges. Pale or washed-out specimens can still hold value if they show rare zoning or clarity, but color saturation drives price. The most valuable material, like that from Artigas, Uruguay, or Four Peaks, Arizona, displays a vivid grape to royal purple with sharp contrast between zones. Next comes clarity. Inclusions are common in amethyst, but high-grade specimens minimize visible fractures, internal veils, or mineral impurities. Eye-clean material crystals that appear clear to the naked eye is favored for faceting. Lapidaries avoid stones with cloudy cores as they interfere with light return. Even specimens with good color lose value if riddled with internal stress lines, which can shatter during cutting. Zoning can work for or against you. Distinct color zoning, such as chevrons or phantoms, can boost collector value, especially if well-formed and centered. But irregular, patchy zoning reduces consistency and is usually undesirable for cutting. Knowing whether a specimen will be marketed as facetable material or a cabinet specimen helps determine how zoning affects its worth. Size amplifies value, but not linearly. A single flawless crystal of 20 grams may command more than a 1 kg cluster full of fractures and pale tips. However, large geodes or plates with undamaged points, especially those lined with deep purple crystals, command premium prices in the specimen market. Museum-quality geodes can exceed $10,000 depending on aesthetics and provenance. Luster and crystal form also matter. Terminated crystals with sharp faces and a glassy sheen indicate slow, uninterrupted growth, often inside geodes. These are highly sought after. In contrast, amethyst in massive form or with etched, weather-worn surfaces is less valuable, though sometimes useful for cabochons or carvings. Finally, origin influences price. Amethyst from specific locations, Uruguay, Russia's Ural Mountains, or Zambia, carries a market premium due to known quality, rarity, or color profile. Provenance matters not just for pricing, but also for authenticity. Buyers often ask for mine or region of origin as part of the value proposition. To maximize potential, document specimens thoroughly. Weigh, measure, photograph in daylight and artificial light, and record exact GPS origin. For commercial samples, consider submitting pieces to gemological labs, like GIA or IGI, for material certification, especially if entering export or wholesale markets.